Welcome to Lecture Online, and now we're going to talk about what we call stellar classifications. It turns out that stars at first appear to be at random in different sizes, different colors, different brightnesses, but with some careful analysis, especially by two very famous astronomers called Hertzsprung and Russell, they figured out how there was a relationship between the temperature and the color of stars and the size of these stars. And the reason why they knew that is because they already were familiar with a couple of laws. One of them was called Wien's law, where there was a relationship between the temperature and the wavelength of the radiation coming from an object, including stars. So the wavelength is then, of course, proportional to the color. And so we knew that there was a relationship between the color and the temperature in stars. Also, we knew Stephan-Boltzmann's law that says that the luminosity, the amount of light, or the amount of energy, better said, the amount of energy coming from a star, was proportional to the emissivity constant, which for stars is pretty well 1, times the Stephan-Boltzmann constant, times the area, the surface area of the star, times the temperature of the star to the 4th power. So, with Wien's law, by looking at the color of a star, we could determine the temperature. And by knowing the area, the surface area of a star, or the size of the star and the temperature, we could figure out the luminosity. Or if we knew the luminosity, we could figure out the size of the star if we knew the temperature. So we began to realize there was a lot of relationships between those things. So what we had to do at that point, and which Hertzsprung and Russell did in a tremendous way, was classify the star. Put a classification on the star in terms of what we call the HR diagram. And you've already seen the HR diagram in some other videos, but again, here it comes back in terms of how to classify stars. So now we're looking at the classification of stars. We now realize that in the upper left corner of the HR diagram, on the main sequence, this is the phase of a star where the star is changing hydrogen into helium. We know that we had very large blue-violet color stars. Then if we go down on the main sequence, they became smaller and just blue. Then they became white, white-yellow, yellow, orange, and red stars. So we knew there was a difference in color. We also knew there was a difference in luminosity. The further up to the upper left corner we went on the main sequence, they were extremely bright. At the very upper corner, they had stars as much as 1,000,000 times the brightness or luminosity of the sun. Here is 1, so imagine this is the sun, a yellow star, and at a temperature of about 5,800 degrees for our sun. So we knew that stars that were up in the upper left corner were hotter, stars that were in the lower right corner were cooler, and so we can then figure out, based upon the temperature, the size, the luminosity, we could find that there's some relationship between the stars, and we wanted to classify them. Ultimately, the classification that we came up with, which we now call the spectral class of stars, and I know that there's a lot of confusion between the terminology between spectral class and spectral type, and we'll get into that in just a moment. And some textbooks, unfortunately, use them interchangeably, which is probably not a good thing to do because it does cause confusion. So let's talk about the spectral class. And to announce the spectral class of the star, we use a lettering system, which is right here. The letters are O, B, A, F, G, K, M. And there's a little sentence that goes along with that. It says, "Oh, be a fine girl, kiss me." Or, of course, you could say, "Oh, be a fine guy and kiss me," whichever you prefer. But you can see that we now have a methodology of classifying stars according to this spectral class. So the very hot stars, the very large blue stars that are still in the main sequence, have temperatures anywhere from 30 to 50,000 degrees Kelvin. So this is in terms of thousands of kelvins. We don't have to say degrees when we talk about Kelvin, but it doesn't matter, it doesn't hurt if we do. And notice that those stars are extremely bright, many thousands, sometimes hundreds of thousands of times the brightness of the sun. So this is a scale of luminosity, which means power or energy emitted by the star, numbers of joules per second. And that would be then in reference to how luminous the sun is. The sun is 1, so this would be 100, 10,000, or 1,000,000 times the luminosity of the sun. Other stars are much dimmer, so 1/100 or 1/10,000 the luminosity of the sun. So notice that the next class is the B class. They're still very large, very bright stars. They're still blue in color, temperatures ranging from 11,000 to 30,000 Kelvin. Then we have the white stars, like Sirius is a white star, and that would have a classification called spectral class A, and that would have a temperature somewhere between 7,500 to 11,000. F, the F-class stars have temperatures of 5.9 to 7.5 thousand degrees. And so notice that those are kind of whitish, yellowish in color. Then stars like the Sun, our Sun is a G-class star. The classification is G. It's a yellow star, temperature of 5,800 Kelvin. Notice it falls right in the range of what we call the G-class stars. Then we have the smaller, orange-looking stars. Those are class star. Those have spectral class K, temperatures from 3.9 thousand to 5.2 thousand. And finally, the smallest stars in the universe, which are also the most abundant. It turns out that the abundance goes up as we go this way. The abundance becomes smaller as we go this way. The most abundant stars in the universe are the smaller red stars, temperatures from 2.5 to 3.9 thousand Kelvin. Notice those are called M-class stars. So that's what we call the classification of stars from O, B, A, F, G, K, M. So when you tell an astronomer, I'm looking at a G-class star, then they realize you're looking at a star very similar to the Sun. If you're saying you're looking at an O-class star, then they know you're looking at a very large, bright, bluish, violet colored star with very high surface temperatures. Notice again that the luminosity, the amount of energy we get from a star, is proportional to the surface area and the temperature to the fourth power. So notice as the temperature goes up, they become a lot more luminous, and also because they get to be bigger, there's much more surface area on those stars. They therefore emit a lot more energy as well. So the luminosity goes up tremendously, exponentially, as we get higher up in the HR diagram of the upper left corner of the main sequence. And of course, the luminosity goes way down when we get to the bottom right. Temperatures are lower and the size is much smaller, so much less luminosity to the stars there. So that's how we classify stars according to their temperature and their color. And so the color is then, of course, associated with the spectral class, and that's what we call it. It's called the spectral class of stars, and that's how we classify stars, at least in the large scale. Of course, we have some other challenges ahead of us as far as classifying stars, but this is the basic way in which we do it. The problem is that, for example, if you're looking at a small red star with surface temperature of 2,500 to 3,900 Kelvin, you say, I'm looking at an M-class star. Well, then you think of it as a small red star. But we also know that on the same color band, same surface temperature, we have some enormously large stars. And they're called red giants. Well, they're called red because they have reddish color, just like the small red stars in the universe. But we call them giant stars because they're enormous. They're no longer main sequence stars. They're now converting helium into carbon, a very different fusion process at the center. Produces a lot more energy. They become a lot more luminous, but they have the same color. And then the question is, how do we differentiate between the small red stars and the very large red giants? Well, we have ways of doing that, and that's part of how we classify stars, part of the stellar classification. So right now we understand stellar classification as far as we call spectral class, which is usually associated with color and surface temperature. And then we'll see how we also classify stars in other ways as well to get a bigger and more, not more accurate picture, but more defined picture so that we can separate between small, subtle differences between stars. So that's where we start. If you're interested in stellar classification, stay tuned. We have a few more videos on the very same topic, kind of delving into it a little bit deeper. That's how we do that. Welcome to Lecture Online, and now we're going to go into a little bit more detail on stellar classification, especially in the area of spectral class. Now, you saw this in the previous video. We have the HR diagram here. We're talking about the stars on the main sequence, how they were separated into what they call their spectral class, O, B, A, F, G, K, M, the different kinds of main sequence stars. So now let's talk a little bit more detail on that. And in addition to that, let's also make mention that we have some that are not really stars. We call them brown dwarfs. And maybe I should write that completely here, brown dwarfs. And these are what we call stars that didn't quite make it as a star. But in other words, there was not enough material to cause enough pressure at the center of the star to start nuclear fusion. To start nuclear fusion, you have to have at least a temperature of 10 million degrees Kelvin. And if the star isn't big enough to begin with, if there's enough mass so that gravity will press the star together to the point where the temperature reaches that 10 million degrees at the center, nuclear fusion never starts. So these are what we call failed stars. They didn't quite make it as a star. And there's three different classes of those. We call them the L, the T, and the Y, brown dwarfs. And notice the temperature for the L-type is from 1.3 to 2.5 thousand Kelvin. For the T-class stars, it's from 600 to 1300 degrees Kelvin. And finally, the Y brown dwarfs have temperatures of less than 600 Kelvin. Now that's still quite a bit. That's still a fairly warm temperature. It's well above the boiling temperature of water. So there's quite a bit of heat being generated there, but not because of nuclear fusion, simply because of the pressure conditions that exist in the star from the formation that it then emits that temperature for many billions of years afterwards. So I should say emit heat for many billions of years afterwards. In addition to that, we also have what we call the S, the C, and the D class stars, and we get into that in just a moment. So what we're going to do here is look at the different classifications, look at the abundance of the star, meaning how many of those stars are there out in the universe, and then how do we recognize them? Why do we call these spectral classes? Well, it's because we look at the spectrum of the stars, the light coming from the stars, and we see very specific identifying what we call spectral lines within the spectrum of those stars that will enable us to differentiate between the different classes. For example, the O-class star, the very hot, very big blue hot stars that are up in the upper left corner of the main sequence, the abundance of those is there's about 1 in 3 million. So roughly 1 in every 3 million stars is an O-class star. So they're very, very rare. They're very large stars. One of the reasons why they're so rare is because they don't last very long. They burn up their hydrogen inside their core so quickly that they typically only last a few million, maybe 5, 10 million at the most years, and then they turn into red giants and then they're no longer main sequence stars. So one of the reasons why there's such a small abundance of them is that they don't last very long. Looking at our sun has been around for almost 5 billion years, so stars like the sun are around for a very long time, so they must therefore be much more abundant on that factor alone. The reason why we can tell that they're O-class stars is because they have what we call ionized helium, doubly ionized oxygen, doubly ionized nitrogen, and doubly ionized silicon in their spectrum. So when we find those spectral lines associated with those ions of those elements, we can then say that that must therefore be an O-class star. So that's how we recognize them. A B-class star, they're much more abundant relative to O-class stars. Of course, they also last a lot longer. B-class stars may last as much as 50, 100 million years before they turn into red giants. So therefore, there's many more of them because they just stick around longer. And so roughly about 0.125% of all stars, 1 out of 800 is a B-class star. We can recognize those on the spectral lines by realizing we have neutral helium, we have neutral hydrogen, ionized oxygen, nitrogen, carbon, and silicon within the spectral line. So that's how we can differentiate between the oxygen and, I shouldn't say oxygen, between the O-class and the B-class stars. Then we have the A-class stars. Those are what we call right here, A-class stars. They're, of course, the white stars like Sirius. The abundance is almost 1% of all the stars, a little bit less, about 2/3% is the abundance of A-class stars. That's where we find stars that have the hydrogen line to be the strongest. So the most recognizable hydrogen lines are found in A-class stars. That's how we recognize them. We also have ionized calcium, ionized magnesium, and ionized iron. So when we see those elements ionized like that, we can, in the spectrum of the stars, we can then say those are A-class stars. The F-class stars, which are the kind of whitish, yellowish stars, a little bit bigger and hotter than the sun, the abundance of those stars is about 3% of all stars fall in that category. The hydrogen lines are somewhat weaker than they are in the A-class stars. We still have ionized calcium, but we also begin to see ionized metals within the spectral lines of those stars. The G-class stars, which is the stars like our sun, the sun, that type of stars is in abundance. About 7.5% of all the stars are G-class stars, so that's almost 1 in 10. The hydrogen lines are weaker again. There's still ionized calcium, but what separates them from the F-class stars is that not only do they have ionized metals, they also have neutral metal lines in the spectrum. So that's when we begin to differentiate them. When we start seeing neutral metals, the spectral lines of neutral metals, then we know we're talking about a G-class star instead of an F-class star. And of course, we also know that the hydrogen lines are weaker in G-class stars than they are in F-class stars. Then we go to the next class, which is the K-class. So we have about 1 in 8 of all the stars in the universe, at least in our neighborhood. So we kind of think that's probably the same in the rest of the universe. Our K-class stars, hydrogen lines are weaker again than in G-class stars. There we see that the calcium lines are the strongest. So when we see very strong calcium lines in the spectral lines, then we know we're talking about a K-class star. We're looking at a K-class star. And there the neutral metals are much stronger than they are in the G-class stars. And finally, for the small red stars at the bottom of the main sequence right here, the M-class stars, notice that about 3/4 of all the stars in the universe are those small red stars. And there we can recognize them from the spectral lines, that we see titanium oxide lines in the spectral lines, and also the neutral metals lines are very strong there, just like they are strong in the K-class stars. But what differentiates between the K and the M is that we see all of a sudden the appearance of titanium oxide in the spectral lines. On the brown dwarfs, of course, those are what we call the failed stars. They never started nuclear fusion. The surface temperatures can be seen simply by using Wien's law. Based upon that, we can kind of see what type of brown dwarfs we're talking about. And finally, there's 3 more classes of stars. There's actually more than 3 more, but the ones that we like to talk about here is the S-class, the C-class, and the D-class. Now, the S-class is a class that's somewhat between the red stars and the red giants. So when we are in between there, what we find is that besides seeing titanium oxide, we also begin to see zirconium oxide. And so that's when we know that those stars are probably on a transition stage between being a main sequence star here and being a red giant. So we call those S-class stars. Then we have what we call the carbon stars. When red giants get to be near the end of their life cycle and a lot of their helium has been converted into carbon, we start seeing very strong carbon lines in the spectrum, and so we call those the carbon stars. So that typically are the red giants are near the end cycle of their life before they become white dwarfs. And finally, we have what we call the degenerate stars, and I think I'm missing an E right here, the degenerate stars, and those are actually, I would like to call them the carbon stars, because those are what we call the white dwarfs. The degenerate stars are what we call the white dwarf stars, when all the outer layers have been spewed out, and what's left there is simply the core, the dying core of a star. When all the nuclear fusion stops, and I guess the reason why they call them degenerate stars is because it's the degeneracy between the electrons, the repulsive forces between the electrons, that keeps them from collapsing even further. So they collapse into small carbon balls called white dwarfs, and those are right in this region right here. The white dwarfs are right in here. So we call this the degenerate stars, because it's electron degeneracy that keeps them from collapsing any farther. I would like to call them carbon stars because they're basically made out of balls of carbon, but it's already decided for me. I can't change that, of course. And so here we have a nice list of the predominant stars in the universe. So O through M are what we call the main sequence stars. L, T, Y are the brown dwarfs or the failed stars. S are the ones in transition from main sequence, from the red kind of stars in main sequence out to red giants. And of course, notice that 3/4 of all stars will go to that stage, because S represents red stars going to the red giants stage, showing zirconium oxide in their spectrum. Then we have what we call the carbon stage, where most of the fusion process is completed, and the core of the star is predominantly carbon, and that's the end stage of the red giant. And finally, the degenerate stars, when they become white dwarfs, and all we have left is a ball of carbon, and all the other layers have spewed out into the universe. And so now we have kind of a good idea of the type of classes there are. So this is what we call the spectral class of stars. We have the ones on the main sequence, O, B, A, F, G, K, M. We have the brown dwarfs. We have the ones beyond the cycle, beyond the stage of the main sequence. And that gives you a pretty good idea of the abundance of the stars as well as how we actually recognize them in their spectrum. When we typically use diffraction gratings. We look at the light, we separate the colors, we look at the spectrum, we look at the dark lines in the spectrum, and we see those particular lines, and that's how we know what kind of star we're looking at. And this is all about classifying stars and being able to identify what we're looking at to help us determine what the luminosity is, what the size of the star is, and so forth. And that's ultimately how we use this knowledge to really understand stars better. And that's how we do that, the stellar classification. Welcome to Electron Line, and now let's take another look at what we call stellar classifications, especially when we talk about spectral class. And of course, the spectral class are represented by the letters O, B, A, F, G, K, M. Those are the typical classification for the stars. And what we do here is we look at the spectral lines of the emissions coming to us. So the light coming to us from the sun and from all the stars in the universe, they have what we call spectral lines in them. Actually, they are dark lines within a continuous spectrum of the rainbow colors of light. And those dark lines are caused by electrons in the atmosphere or in the outer layers of the stars being excited and jumping up to higher levels, then back down to lower levels. They're caused by the photons coming from inside the star. When they hit the electrons in the elements on the outside of the star, the electrons, they jump up, then they jump back down, and when they jump up, they absorb those photons, and so those are then the missing colors, the missing lines that show up as very dark lines in the spectrum of the stars. The sun has over 800 of those lines, all contributed to various elements within the sun. And the reason why we can recognize what elements are there represented by those is by the specific, what we call the specific colors that are then associated with specific wavelengths, which are then associated with specific energy level differences in the electron jumps in the outer orbits of those atoms. The ones that we specifically look for are helium, hydrogen, silicon, magnesium, iron, and calcium. And then when we talk about the M-class stars here, we also look for titanium oxide. And you can see that depending upon the temperature of the outer layers of the star, the O-class stars, of course, are very hot. The B-class stars and A-class stars are also fairly hot. And because of that, we have different kinds of electron jumps caused by the photons reaching those outer layers. And so, for example, you can see that we have silicon, ionized silicon, but the ionization here causes silicon to lose 3 electrons. Here silicon loses 2 electrons, and there silicon loses 1 electron. And we can actually differentiate between what class of stars we're looking at by noticing which of the electron jumps are occurring in the outer layers of the star, which then causes certain wavelengths to be absorbed associated with those specific electron jumps. And from that we can actually determine what class of stars we're looking at. Notice when we start looking at the A and F and G class stars, the hydrogen lines become fairly prominent, so they become much darker, much wider, and so easily visible. And by measuring the relative strength, and as you can see, the vertical axis here is the relative line strength. When we look at the relative strength of the lines caused by the helium, the electrons in the helium or the hydrogen or the magnesium, when we line those up, we can see that as we go from B to A to F class stars, the helium lines become weak and the hydrogen lines become stronger. The magnesium lines reach a peak and then become weaker. And then if we go further, the F and the G class stars, notice that the calcium +1 line, so this is where we have 1 electron missing, that the calcium +1 line starts getting stronger, stronger, stronger as the hydrogen lines become weaker. Then if you continue to go to the right and get to cooler class stars like the G and the K class stars, notice then that the iron +1, where 1 electron is missing, or neutral iron, become more prominent in the line structure of the spectrum that we get from the stars. And so by measuring the relative strength of these lines, we can then determine what class star we're looking at. So not only do we determine the class star by the surface temperature, which is associated with these classes right here, we can also do it by looking at the spectrum and do an analysis on the spectrum and notice which dark lines appear strong and which appear weak. Also notice that the neutral calcium line becomes stronger and stronger as we get cooler and cooler stars, and eventually when we get to the cooler M-class stars, we see titanium oxide appearing in the spectral lines. So that's actually a really good way for us to double check to see what class stars we're looking at. It's not always an exact science. A lot of these are approximations. Sometimes they're difficult to see because of the relative abundance of some of these elements in the stars, which makes it difficult as well. And then it turns out so that in order to do a good job in trying to figure out what actual star, what type of star we're looking at, we look at the surface temperature using Wien's law. We look at the color combination through special filters, the UV filters, U for UV, B for blue, and V for visible light filters. And we combine all that information to try and narrow down exactly what type of star we're looking at. This is indeed a very good tool by just simply looking at the spectral lines. Of course, it's not an exact science, and sometimes we have to cross-reference multiple measurements in multiple experiments to see what class star we're actually dealing with. So that's how we do that, and this gives us a nice visual representation as the surface temperature of the star cools down, which of the electron jumps will become more prominent in the spectral lines, and by doing a combination of looking for these various jumps in these various wavelengths, we can actually see how the determination can be made looking for the particular class of stars. In order to be able to get a more accurate feel or say about what actually we're looking at, what we've done is we've taken the classification of the stars, the various classes, O, B, A, F, G, K, M, and actually subdivided them into what we call spectral types. For example, we have class A0, A1, A2, so we can actually subdivide this even a little bit more carefully, and so we call them the spectral type, narrowed down to a very small fraction of each class. We'll see that in a future video, how that is done. But you can imagine that, yes, as you move over from A to F, in that region here, you can see that the spectral lines will begin to change quite a bit, and we are actually able to pick that up and actually subdivide the classification even more finely than that, and that helps us determine what exact star we're looking at. So that way we can match up the exact temperature with the exact class and type, as well as the coloration that we get through the various filters. So it's quite a job to try and figure out, when we look at a star, analyze the light coming from it, to know what exact type of star and class star we're looking at. So that's how we do that, and this is what we call spectral class searches, through looking at the spectral lines in the spectrum of a star. That's how we do that. Welcome to Lecture Online, and now let's try to figure out what the difference is between a spectral class and spectral type. So here we're going to try and illustrate what a spectral type is. And unfortunately, this is quite often in all kinds of reference material, books, and on the internet, used interchangeably, and that's why it's so confusing. So what we mean by spectral class, where we have stellar classification and we classify stars according to this stellar classification. So we have the O, B, A, F, G, K, M for your typical stars on the HR diagram. And so we have the associated electron jumps, which gives us their specific wavelengths associated with those jumps, photons that get absorbed coming from the inside of the stars. And by those missing colors, those missing lines, we can identify what spectral class of star we're dealing with. But you can see that there's a lot of variation between B, A, F, G. There's a lot of space in between. You can see how the spectral lines do change considerably, going from F to G and from G to K. And so we want to be able to identify that even more accurately. And so we've subdivided the stellar classification by some numbers. Starting from 05, we go to 06, 07, 08, 09, to B0, B1, B2, B3, B4, B5, B6, B7, B8, B9, then to A0 and so forth. So we subdivided every stellar class in 10 gradual changes, each represented by a number starting from 0 through 9, and then we get to the next stellar class. Those subtypes are called stellar types. So that's where the difference comes in between stellar class and stellar type. Again, it's often used interchangeably, unfortunately. But so when you talk about our sun, for example, our sun is a G-class star, but it's of type G2. It's not a G1, it's not a G3, it's exactly a G2, which is associated with a temperature of just under 5,800 degrees Kelvin. And then if you can look over here, you can see that it has a fairly good distribution of the calcium +1 line, the hydrogen line, the iron +1 line, and the neutral iron line, and a very small amount of the neutral calcium line. So those lines are visible in the spectrum, and by doing that, by making measurements accurately of the width and the what we call the line strength, the intensity or the boldness of the line, so to speak, within the spectrum, we can identify that our sun is indeed a G2 type star. So that's what we call spectral types by using that subdivision on the classes. It makes it a lot easier because there's a lot of difference between, for example, a G2 and a G6 star. They're both of the class G, but there's a significant difference in the line strength of the particular elements. Notice that for the 6, the calcium becomes stronger, the hydrogen becomes weaker, and both iron +1 and iron neutral become stronger as well. And so we can see those differences, and therefore we have kind of subdivided the class into those particular types, which makes it easier to say, now I know exactly what star you're looking at based upon the typing of the different classifications. So spectral class, we have the letters O, B, A, F, G, K, M, And the spectral type is a subdivision of those classes into smaller bands where we can more accurately describe what type of star we're looking at. And that's the difference between the two. That's what we mean by spectral type. Welcome to Electron Line. Now we're going to talk about another type of classification called luminosity class. It was recognized initially when the HR diagram was devised and they started using it, how useful it was in determining the type of star we were looking at, because the vast majority of the stars were on the main sequence, and so they fell into a very nice categorization where we have the spectral class O, B, A, F, G, K, M, and the spectral type, the subdivisions of these classes. And then we were able to find out exactly what star we were looking at by looking at the spectral lines, and we could see how different elements in an ionization state would appear on the spectrum. And by analyzing that, and by analyzing the light coming from those stars and setting it through UBV filters, and by looking at the temperature of the stars using Wien's law, we could really figure out what type of star we were looking at. But once in a while, we would look at something that, even though the color and the temperature seemed to match, the spectrum of these stars were looking very different. And we weren't quite sure what that was and what the reason for that was. And then we began to realize there was also some different types of stars that had the same surface temperature and the same color, but had a very different spectrum. For example, if you look at the M-class stars, we know that these typically are very small, reddish-looking stars. They become smaller and smaller, so we go down on the main sequence. But then, with the same surface temperature of roughly 3,000 degrees, 3,000 Kelvin, we noticed that there were some other stars that were up in these regions right here. They were very luminous, and yet they had the same surface temperature and the same colorization, but of course we had these extremely large supergiants, we had large giants, we had some subgiants. They all had the same color, same temperature, and we had to find a way in finding the difference between the stars by looking at the spectrum. And we began to realize that we could actually do that. We could subclassify them, and so we came up with what we call the luminosity class. So in the supergiants, and of course they range in color all the way from blue to red, we had two subdivisions. We call them the very luminous. So we had these very luminous supergiants, and then we had what we call the luminous supergiants. Oops, I guess I already have the word supergiants up there. And so we call those the luminosity class 1A and 1B. So those became 1A and 1B. And then we had a class, so then we looked at the giant stars, the red giants, and we saw that there's some very big red giants, not quite as large as the supergiants, but bigger than the typical red giants, so we call those the bright giants. And that became luminosity class 2, and they fell a little bit lower on the HR diagram in the luminosity scale. Remember, when we go up, it is greater luminosity. When we go down, small luminosity. So we call those the very bright giants. And so that was the very luminous supergiants, the luminous supergiants, the bright giants, and that was then the luminosity class 2, and we used the Roman numeral type of way of classifying those. Then we had the class which we call the regular type of giants, so that was luminosity class 3. And then we had a class of giants which were not quite as big as a typical red giant, but they were much bigger than the main sequence stars, so we call them subgiants. And those also could be recognized as having a different spectrum, so we call that luminosity class 4 for the subgiants. And then finally we end up on the main sequence, where of course the vast majority of the stars are, and so we call that luminosity class 5. So when we talk about a luminosity class 5, we talk about a main sequence star. And then we realized there were some stars that were kind of like main sequence stars, but not quite of the same size and coloration and spectrum as the typical main sequence stars, especially in the region of the red dwarfs, if we want to call these red dwarfs, because they're small red stars. We have what we call the subdwarf category, and so for that we had a luminosity class that was known as luminosity class 6. And finally there was one more star on the main sequence that we had not accounted for yet, the very small, hot on the surface stars that are down to the size of about a planet like the Earth. And so we would then have a 7th luminosity class, which would then be recognized as being the white dwarfs. And again, they have a very different kind of spectrum as the other stars on the HR diagram. So all we had to do is actually recognize which stars we're talking about based upon the spectrum, and then we could classify them. We're actually able to do that. So we now have what we call luminosity class. This is then combined with the spectral class and the spectral type, and from that we're able to really recognize what stars we're talking about. And so that's what we mean by the luminosity class. Welcome to Lecture Online, and now let's see if we can make sense out of the spectral classification. So we have spectral class, spectral type, and luminosity class. So here we have stars, a list of stars, some of the more famous stars around, some of the most known stars. And so we have the first letter represents the spectral class. Then we have the number here that represents the spectral type along with the letter. And then we have the luminosity class. And from that we should be able to figure out what star we're looking at. For example, our sun is a G2 5 star. Well, the G means spectral class G. The 2 means spectral type 2, so G2, and the 5 means that's a main sequence star. So when we go to the HR diagram, we can see that the G2 is right about here, luminosity equal to 1, so that here represents our sun on the main sequence. The 5 indicates that it's a main sequence star. That's a luminosity class for a main sequence star. So here we have Sirius A, the brightest star in the sky, which is part of Canis Major. So it's also known as Alpha Canis Major. Now Alpha is the first letter in the Greek alphabet, which then indicate that it's the brightest star in that constellation Canis Major. So instead of saying Sirius A, we can also say Alpha Canis Major. It's the same star, and its classification is A15. So A means that it's brighter, bigger and brighter, and more massive than the sun. So notice that the A is over here, surface temperature of about 10,000 Kelvin. Now notice that A will go from A0 to A9. By the time you get to A9, the surface temperature is about 8,000 Kelvin. A0, the surface temperature is about 10,000 Kelvin. So you see that A1 would indicate that it's just slightly less than 10,000 degrees on the surface temperature. And 5 means that it's also a main sequence star. So it looks like Sirius would be somewhere in this region on the HR diagram. All right, next one is Arcturus. That's the very bright star in the constellation Buddha, so we call it Alpha Boötis. It's the brightest star in that constellation. Notice that the classification gives it a K 1.53. 3 means that's no longer a main sequence star, it's now a red giant, so it's a red giant. K means that it's a orangey looking red giant, and 1.5, so it's one of the hotter K class stars. 1.5 is just slightly to the right from K0, so it's probably surface temperature maybe around 4,800 degrees. Puts it in as a red giant, so it would be about right here. So that would be Arcturus, would end up over there on the HR diagram. Arcturus is about 33 light years away from us. You can see it, it's very bright, even though it's fairly far, because it is a red giant. Vega is the bright prominent star that's directly above you during the summertime. It's Alpha Lyrae, and it has the classification A05. Now notice that's very similar to A15, so that means that Vega and Sirius are very similar stars. We can then say that Vega is just slightly hotter, slightly bigger than Sirius. So Vega would appear somewhere around here on the main sequence. So it's kind of interesting to realize now that Vega and Sirius, two of the brightest stars in the sky, are very, very similar based upon their classification. Here Capella is a G5 class star. So the first thing you would say, oh, wait a minute, or I should say G5, the type G5. You say, well, that's very similar to the sun, until you see the luminosity class. Here you realize that color and surface temperature are probably very similar to the sun. However, this indicates, luminosity class, that it's a red giant, and the sun is a main sequence star. So that means that it'll probably be somewhere in this region right there, and that would be for Capella. Capella is the brightest star in the constellation Auriga. So again, the alpha indicates that it's the brightest star in that particular constellation. Now here's an example where we have B Orion, and here we have Epsilon Cygni. Epsilon, let's say we have alpha, beta, gamma, delta, epsilon. Epsilon is the 5th letter in the Greek alphabet, which would indicate that this star is the 5th brightest star in the constellation Cygnus. Now notice I don't have a name associated with it. It may have a name. I don't know that particular name. I may be able to look it up. But sometimes it's sufficient to say just the Greek alphabet and what constellation it belongs to indicate what star we're talking about. Okay, so we had the next one was Betelgeuse, a very bright star in Orion. We called it Alpha Orion. Now here's an interesting point, because Rigel, which is also a star in Orion, is actually brighter than Betelgeuse, but yet it is designated as Beta Orion, where Betelgeuse is designated as Alpha Orion. Maybe that should be flipped around, but there may have been a time that Betelgeuse appeared brighter than Rigel. It is kind of difficult to measure the brightness of Betelgeuse because it's a variable star and it changes in brightness. But nevertheless, they're very close in brightness, so we call this Alpha Orion and Beta Orion. Notice Betelgeuse is an M1 1AB. What does that mean? Well, M is an M-class star. M1 is just to the right of M0. So the surface temperature is probably just slightly over 3,000 degrees, because the 3,000 degree mark starts like maybe at M2, M3. And then it says 1AB, so that's luminosity class 1, which makes it a supergiant. And AB, A is a very luminous, B is not so luminous supergiant, or sometimes it's called luminous and less luminous supergiant. So it's somewhere between very luminous and not so luminous supergiant. And M1 gives it the reddish color and gives the surface temperature just slightly over 3,000 degrees. Rigel is a B8 1A. Now 1A means it's a very luminous supergiant, but notice the class is BA, or the type is BA. We call it class when we just say B, the type when we say B8. And notice B8 would put it just to the left of A. That puts it up here. So this would be Rigel right there. And so Rigel has a whitish bluish color, if you look at it, where if we look at Betelgeuse, it has a reddish color. So Betelgeuse would be up here somewhere, and so that would be Betelgeuse. And that has a reddish color versus a bluish whitish color for Rigel. Notice that, let's see, surface temperature of a B8 star would be more than 10,000 degrees. So Rigel is a supergiant, bluish looking star. Surface temperature very, very hot compared to the surface temperature of Betelgeuse, which is slightly over 3,000 degrees. Then we look at Regulus, which is the brightest star in the constellation Leo, so we call it Alpha Leo. It's a B7 5 star. 5 again means it's a main sequence star. B7 means it's fairly large and very bright. So notice that it's very similar as Rigel as far as color and surface temperature is concerned, but Rigel is a supergiant where Regulus is a main sequence star, so obviously it will be a lot smaller, but B7 still means that it's very hot star, maybe 12,000 or so, 13,000 degrees on the surface, but it's a main sequence star. So there you can see that the classification stars really helps us. Even if we didn't know what the names were, what constellation they belong to, and we just look at this portion alone, we should be able to tell now whereabouts that star should be located on the main sequence. We know about what the color is, sizes, mass, and surface temperature, and then if you know enough about the spectrum of stars, then you can say, well, the spectrum will look like this. Of course, that's kind of a stretch for most of us because we're not that intimately familiar with the exact spectral lines of every different type of star that's out there. But at least gives you a really good idea of what we're looking at, simply look at when we look at the stellar classification. Hopefully that helps. Now you know all about what the star is like by simply look at the classification. That's how we do that. Welcome to ilectureonline, and now let's take a look and see how they determine the various luminosity classes. We may wonder how they determine the difference between a main sequence star and a giant star when the colors are the same. For example, we may have an M-class star. It could be a main sequence star. It could be a red giant. How do we tell the difference? Well, it turns out that they may both have the same surface temperature and they may both have the same color, but the density of the gases in the outer layers of the stars are very different. A red giant is enormous in size, and the layers on the outside, where the photosphere is, where you can see the surface of the star, they're very tenuous. So we have very low density low pressure gases at the surface. So we have low pressure and we have low density, and the result of that is that the signature in the spectral lines is much less pronounced than when we have stars like on the main sequence, where we have high pressure and high density. Of course, that is relative, because at the photosphere of even main sequence stars, the gases are not very dense compared to what we're used to with atmospheric pressure here. But in comparison to the giant stars, the density and the pressure is much higher. So we have high density and high pressure, relatively speaking, at the surface of stars on the main sequence relative to subgiants, giants, or supergiants. So high density and high pressure. So we're actually able to see the difference in the pronunciation of the what we call the missing lines, the missing colors, the spectral lines that are missing in the rainbow of colors coming from the stars. Now, the reason why those colors are missing is as the photons are trying to escape the star, trying to make it through the outer layers, and of course a lot of the elements, a lot of the material in the star is hydrogen. You can see that hydrogen has a single proton and has all the various what we call energy levels that the electron can be at. And as the photons stream through the outer layer of the atmosphere or the outer layer of the star, the photons collide with the electrons and cause those electrons to jump up to higher levels, thus absorbing photons of very specific wavelengths and color. For example, when a photon comes in and hits an electron at the second energy level and causes it to jump up to the third level, it'll absorb a red color wavelength of 656.3 nanometers, so that's color simply absorbed. If a photon hits it with the exact amount of energy and causes it to jump to the third level, right, or I should say fourth level right here, then it absorbs kind of a blue-greenish color, and that color is missing. If a photon comes along with the right energy and hits an electron in the second level, causing up to jump to the fifth level, it absorbs a purple color. And then if a photon comes along, hits an electron in the second level, causes up to jump to the sixth energy level, again it absorbs a purplish UV type of color. And so those are simply absorbed, and those then show up as missing lines on the color spectrum of stars. Now here we have what we call the H gamma line and the H delta line. The H gamma line corresponds to an electron jump from the second level to the fifth level, and an H delta line corresponds to electron jump from the second level to the sixth level. So those two lines simply would be gone. Those would then be purple colors. They would be gone, and you see a black line. But for the giants and supergiants, those missing lines are very thin and tenuous. They're not very pronounced. For main sequence stars, they're very thick and very pronounced for stars of the very same color. So as the lines become thinner and thinner and thinner, we can then imagine that these are higher and higher luminosity classes. So from the main sequence being class 5, we have the subgiants class 4, giants class 3, and then we have the luminous giants, which are, or the bright giants as we call it, which is class 2, and then the very luminous or luminous supergiants, class 1a and class 1b. And so therefore, we can subdivide that in those various luminosity classes just simply by looking at the spectrum and see how pronounced those various lines are for stars of that particular color. Of course, we also know that they vary according to their spectral class, but we have to differentiate between the variation due to change in the pressure and density of the gas at the surface versus change in the temperature of the surface as the stars get hotter and hotter as we go from M-class stars all the way up to O-class stars. But we're able to do that, and from that we're able to determine what type of luminosity class we're looking at, and therefore we're able to place the stars we're looking at exactly on the HR diagram as they should be, based upon the determination of the luminosity classes, based upon the pronunciation, I should say, or how well the spectral lines are visible on the spectrum. And that's how we do that.